last lecture we were explaining simple harmonic motion when we said any motion that follows a sine curve is a simple harmonic motion, and we wrote the equation as a sine omega t, where we explain omega to be the angular frequency and a was the amplitude. So omega, and we also explained terms like frequency and time period, and they were all related with omega. And this is how a was defined to be the maximum value the wave, the motion achieves, is called the amplitude. There can be one more addition to this expression or this formula, that here we are assuming that the motion starts at 0, which means if you have let's say an example of simple harmonic motion, a spring mass system, and this is lying in gravity at rest, and if you pull it down, then it oscillates up and down. And if you start recording the um, the motion of this object, then let's say you can also say that you have started recording the motion from the lowermost position, then your graph should actually look like something like this. You start with the maximum because you have stretched the spring maximum, and then the simple harmonic motion follows. So this motion contrasts this one in the case that here you assume that you started recording your motion from this situation, while here you assume you have started your recording from this situation, or you have started describing the system from this situation. As a matter of fact, if you start describing the motion from this situation, which means the string is compressed in the upward direction, then the whole thing will look like something like this. It's a sine wave. Please assume it's a sine wave. It's not really a sine wave. I'm trying to draw a sine wave, but it's a sine wave. So these, you see, this formula is not complete. It needs to be modified a little to include cases when you start recording your data or start explaining your motion, not just when you are in this position, but anywhere between minus a to plus a, if you define this as the positive x-axis. And this can simply be done by including something called a phase. Now at t equals 0, you can write x equals a sine phi, which has some value. It can have any value between minus a and a, depending what phi is. If phi is 0, then the x is 0, which means this case is with phi equals 0. What is phi here? Well, phi is pi over 2, because you know that a sine omega t plus pi over 2 gives you a cos pi over omega t, which is nothing but this motion. And what is phi here? In this case, phi is 3 pi over 2, because that a sine omega t plus 3 pi over 2 is going to be minus a cos omega t, and which is this motion, and anything in between also. And phi can be between 0 and 2 pi. So this is the most generalized equation of a simple harmonic motion. The simple harmonic motion follows this equation, and this is the most general equation for that. But the question is, what kind of systems will produce this kind of motion? We have said this is the motion this is the motion of a simple harmonic system. But what is the physical condition that will produce this kind of motion? So now we are stepping into more mathematical understanding. So let's talk about that. Okay, so mathematically, simple harmonic motion is produced when restoring force is proportional to the distance from the central point. What does that mean? For example, we have a spring mass system, and this is the let's say this is where it rests. This is the unstretched position. The spring is unstretched. But if you stretch the spring such that it starts oscillating, let's say this is the mean position or the central point, so that it starts oscillating up and down, you know that at any point which is at a distance x from the central point, the force produced by the spring is nothing but minus kx according to Hooke's law, which means this is the restoring force. Why? Because there's a negative sign. There's a negative sign here. So the motion is in the positive x direction, but the restoring force is acting in the negative x direction, or the force is acting in the negative x direction, which means the restoring force is trying to restore the motion. Restore the motion. Okay, and we also know F is given as ma. So you can write ma equals minus kx, and because it's in one dimension, you can sort of also rewrite this as ma equals minus kx. We're not worried about vector sign right now because we are moving in the x direction. And you know that a is dv over dt and v is dx over dt, and in a combined way a can be written as d square x over dt square. So you can write m d square x over dt square equals minus kx, and that gives you d square x over dt square plus kx equals 0, which means d square x over dt square plus k over m x is 0. Now you can define k over m as omega square, and you get this as your differential equation. This is the differential equation which this system is following. And any system that follows this differential equation is called simple harmonic motion. And the solution of this equation we already have discussed is given as ax equals a sine omega t plus phi. Now this is the distance of the object from the central point. You can also find the velocity, and this is a function of time. You can also find the velocity, which is given as dx over dt, and that gives you a omega cos omega t plus phi, and also the acceleration, which is d square x over dt square equals a minus a omega square sine omega t plus phi. So these are the various variables. Just to comment on this equation, whenever you have a problem on simple harmonic motion, you are basically trying to achieve this equation. Now variable can be x for this kind of system, it can be angle, let's say for simple pendulum which moves angularly, and we'll talk about that. And you can have other cases also. So, but this is what you're trying to achieve, this kind of equation on variable x, theta, or anything else. We'll talk about that. This is the kind of equation you're trying to achieve when you are trying to trying to explain a simple harmonic motion. And omega is called the angular frequency, which we already have discussed. So omega, you know, is root k over m. And you can also notice from these equations that if x is pointing in this direction, then velocity is in this direction and acceleration is in this direction. What does that mean? It means that if x is minimum, then v is maximum, or velocity is maximum. As you can see, velocity is maximum at the central point, and velocity is maximum at the central point, but x is minimum at the central point. Similarly, if x is maximum, then a is maximum in the opposite direction, which means if a string is completely stretched outward, which means x is maximum, then a is maximum. You can see that if the spring is stretched maximum, it's going to produce the maximum force, but in the opposite direction. And that's why a is maximum in the opposite direction, which can be understood from these graphs. If we draw these graphs, we'll see that if you draw these graphs, and this is how x behaves, then your acceleration, let's change the color here, then your acceleration is going to behave like this. It's for the same time. We are actually, this is the time. So this is x, this is v, and similarly I'm sorry, this should be actually acceleration, and similarly the velocity. The velocity should be actually like this. It should be like that. This is the velocity. So when both acceleration and distance are 0, velocity is maximum. So both distance and acceleration are 0 at central point, and velocity is maximum at that point. This is velocity. So this is how these three things vary in time. And this is sort of a summary of simple harmonic motion. The summary is this. This is the equation simple harmonic motion follows. This is the solution of the distance or any variable that is causing the simple harmonic motion, or the variable which is changing. It's the variable which is changing, uh, and a is the maximum value of that variable. In this case, it's distance. Omega is the angular frequency by which that variable is changing or completing cycles. Phi is the phase, which tells at what value does the variable x start with. And similarly, these are velocity and acceleration, uh, and these equations tell the time dependence of velocity and acceleration. So we will take some examples in the coming lectures, where we'll try to achieve these kind of equations and try to find omega or the angular frequency, and things will become more clear.